Welcome to lesson 6 of my refresher course. Today I'm going to be talking about sequences and series and proof by induction. I don't think I'll get to any exam questions today because there's quite a bit to cover in this. It's when it comes to sequences and series, it's all okay. The main ones that we'll focus on will be arithmetic and geometric sequences and series. We'll talk about them. They're quite simple, so I'll just explain like kind of what they are and why we might like to use them. And then after that, we're going to talk about proof by induction, which is just the thing about proof by induction is that no two proofs are ever the same. So that's what like you can't. It's not something you kind of really learn off, right? But there are 3 steps, and I'll show you the 3 steps. And once you understand the 3 steps, then you're going to be able to handle the kind of the more awkward ones that they give you. So first of all, let's talk about the following sequences, and we're going to try and classify them as either arithmetic or geometric. So when we talk about a sequence, basically we're talking about a list of numbers that just goes on basically forever, right? Now you might think like, why would you want a list of numbers that goes on forever? So like we could have one second. Just need to open up pen software so this works. So we'll just have like what we do sometimes is we have this sort of curly set of brackets, and then we have a list of numbers. Could be like 1, 2, 3, 4, 5. And what we do is we put down these 3 dots at the end and kind of close the bracket then at the end. And what we're saying with these 3 dots is that it just keeps going on and on and on. So that's what all of these here mean. And the reason why we might want to list, an infinite list of numbers is because this is about it's about kind of like sort of taking steps into the future, maybe, right? So you could be talking about, if you were in finance, you could be talking about, what's the price of such and such today, and what's the price of it tomorrow, and what's the price of it the next day, and you make a model that will go into the future, and you can look at that model and you can see if the price is going up or if it's going down or something like that. Or you could be sending like a satellite to go in orbit around like a planet or something like that, and it's on its way, and you're thinking, okay, tomorrow it'll be here, the next day it'll be here, the next day it'll be here, and we're actually going to miss if we keep on going on like that. So I'm going to make a change today that will sort of so it's about kind of like, you use it a lot in computer science, about kind of like having algorithms that like, sort of like they're sort of looking ahead and stuff. Like what I'm saying here is like, don't take it to the bank. I'm just giving you a little something to kind of think about why we should care about this thing at all. Um, okay. And now that we have sequences that go on forever, oh, by the way, the series is just then when you add them up, right? So this would be like a term, the first term, the second term, the third term, the fourth term, and the sequence. But then S1, S2, S3, S4, S5, these are different things. S1 means add up all the numbers from the start up to the first one. Okay, so it's the first one. S2 would be, well, add up all the numbers in the sequence up to the second one. That'd be 1 plus 2. Then S3 is 1 plus 2 plus 3. And S4 is 1 plus 2 plus 3 plus 4. And we can have a way to kind of think about this later. So the sequence is the list, and then the series is some of the list. And we have different ways of generating sequences, and the main 2 that we look at, but it's not the only 2 on leaving cert. They give you other ones that don't have a name, are the arithmetic sequence and the geometric sequence. And basically for the arithmetic sequence, you're always going to have a starting number, and then what you're going to do is you're going to add on a number to get the next number. And then you're going to add on the same number to get the number after that. And you're going to add up the same number to get the number after that. So you can see the starting number, which we'll call A here, is 2. And the adding number, right? These are not minus signs, incidentally. They're just like bullet points. The adding number, which we'll call D, is 3. So this is 2 to 5 is 3, 5 to 8 is 3, 8 to 11 is 3. And we have something like a step of stairs where, we go along 2, but we go up 3. We go along 2, but we go up 3, right? Sorry, what am I talking about? We start at 2, and then we go up 3, then up 3. So it's something like a step of stairs, right? Where we just keep going up by an even amount, okay? Okay, so have a look at the second one, right? So the starting number is 3, right? And the gap here is 3. And then we look at the next number, and the gap here is 6. And we have a look here at the next one, and the gap here is 12. So it's not staying the same if we're adding, but what if we were multiplying? So let's have a look here. To start at 3 and to get to 6, we'd have to multiply by 2. Here we'd have to multiply 6 by 2 to get 12. So this is actually a geometric sequence. So this is let's underline that one with that. This is a geometric sequence with A is equal to 3 and OR is equal to 2. Okay, so starting with 2 and adding on 3 each time is a rule that we can use to generate an infinite list of numbers that goes 2, 5, 8, 11, 14, and goes on forever. It's just a simple rule, and it's like adding, and for some reason they give it a fancy name called arithmetic sequence. And then for the geometric sequence, it's the same thing. You have a starting number, but instead of adding each time, you multiply each time. Okay, now have a think about the second one. Again, these are not, sorry, but I'll have to just remove these things here. It's confusing. Okay, so have a look at the next one and just have a think to yourself for a moment. What about this one? Is it going to be arithmetic or geometric or neither? And if we look at it, well, if it was, let's say the first number on the list, I use a different color this time. We don't know. A is equal to 1. And in order to get from 1 to a half, well, we have to multiply that by a half. And in order to get from a half to a quarter, we have to also multiply that by a half, right? A half of a half is a quarter. And then we have to multiply that one here. And this is OR is equal to a half. And so this here is, we can see that this is a geometric one. This is a geometric one. This was arithmetic, okay? And we could already see something that's kind of interesting from about geometric sequences. And here, that is, for this list, the numbers keep getting bigger. And that's because the multiplying number is greater than 1, or is greater than 1. And here they start getting smaller. So this is, or is less than 1, right? And so when the numbers when OR is less than 1, then the numbers get smaller. And what we can say is basically, I'm going to do something here. I'm going to say basically that, I'll write it in words. This sequence tends to 0, but this sequence tends to infinity. Okay, so this one here is blowing up. It's getting larger and larger and larger. And if we keep on going down the list, we'll get ever bigger numbers. And if we keep going down the list here, we'll get ever smaller numbers. And if there was a possibility to get to a destination, which there isn't, because we can never complete writing down an infinite list of numbers, then it would be 0. So this arrow here means that it's going to 0, and this one means that it's going to infinity. Okay, we have a look at the last one. So we start off with 2. So we've got an A is equal to 2. And then we have a jump of 3. No, we have a jump of 2. Then we have a jump of 3. And then we have a jump of 4. And we don't have a multiplier. So this is like neither arithmetic or geometric. So it's some other rule that we don't study on Lebensjahr. And it says name the common difference D, or the, yeah, so that's what they were saying also too. The common difference is D for the arithmetic sequence, and the ratio is, the common ratio is OR. So we have a D and an OR and an OR. Okay, so now what we're going to be using an awful lot with sequences and series is we're going to be using subscripts, right? Because if we have a list, we'll have an A1, an A2, an A3. And, you know, superscripts obviously mean powers, but the subscript means the first number in the list, the second number in the list, the third number in the list, okay? This is just notation, but I promise you it's much, much quicker to write it like this than to say it in words. Like okay, the first number in the list is, you know, everything else besides using subscripts will be longer. That's why we will use them. And then the series, now this is the series up to n. And what we're saying here, you see this, we can have a list that goes up, let's say this list, that's A1, A2, A3, all the way up to AN, and then we keep on going. So the point is that this AN is somewhere in the list, basically, right? Like it could be the 10th number, the 20th number, we don't know, right? But here, this would be, if we were to sum up to AN, then we would have to add up all the numbers below n up to n, right? So that would be the series, the sum of the sequence, okay? And what we want to do is we want to be able to write down an expression for an today. So if I tell you, let's say if I gave you an arithmetic sequence, which has a first number, which is 2, and a common difference that's 3, then I can start writing out the sequence. I can say the first number is 2. Well, add on 3 onto the 2, I get a 5, and I get an 8, and an 11, and a 14. And this is now, let's say, this is our sort of, what would we call this? A1, A2, A3, A4, A5, and so on. Now, what if we want to get up to A10? You see, using this method, we have to calculate, we have to figure out all the ones before A10, right? So if we write out a formula for AN for the terms in the sequence that only has N in it, then we can jump to any point in the sequence that we want. So this could be like, these numbers, 1 could mean, day 1, 2 could mean day 2, 3. So we might want to know what happens after 20 days. So it would be nice to have to be able to jump straight there, or the sum to 20 days or something like that. Okay, and then so I will be able to write down an expression for n, and then the other thing is we're going to look at infinite sums, and we'll talk about that now in a minute as well. Okay, so for the arithmetic sequence, and this is a formula that's in the tables as well. Sorry, I really should have gotten rid of that. So if we look at the tables here, which page is it on? Sequences and series on page 12. So the good news here is that you have these formulas. It's page 16, page 12. So we have the formulas for the arithmetic sequence and for the geometric sequence. So let me just take these across. So we have these formulas. Okay, so what we have here, and you already noticed a little bit of a, let's say we've been talking about AN, okay, like here, right? But the book calls it TN. It's the same thing, like when it comes to the name that you give something, like you can think about T as term. So the sequence I was saying, like A1, A2, A3, and so on, But you could also say term 1, term 2, term 3, and so on, right? So it doesn't, that's just notation. That doesn't matter, right? So here in the notes, then you can see that they're using TN instead of AN. But what they have here, you see this here, this is a formula, and this formula has an A in it, which is the first number. It has a D in it, which is the common difference. And then it has this N. And if I want to work out T10, the 10th number in the sequence, I put a 10 here, and I just put a 10 here. And then I can just jump to that number. Okay, so that's all that formula does. And then this one here is this is the sum, basically, up to like, so S10, I just put in 10 in here. Okay, now we can derive these formulas. I'm not going to do that today because this is just a sort of refresher, right? So we want to get through as many questions as can to remind you of everything. And then for geometric sequences, we have this one here. Tn is a times or to the n minus 1. So T10 here would be a times or to the 10 minus 1, which would be a times or to the power of 9. And then the sum to n would be a times 1 minus or over 1 minus or to the n over 1 minus or. So we'll talk about these as we come to them. Okay, so let's have a look at this one here. So this is the formula that we can use then for arithmetic sequences. So if we had an arithmetic sequence with the first number in the list being 4, and then the common difference being 3, then we could calculate A15, the 15th number in the sequence, by taking this formula here. So we have to sub in for A, which is 4 plus, and then n minus 1. So that's 15 minus 1 times 3, which is then 4 plus 14 times 3. And then 14 times 3 is like 42. So this is like 46. So we can get that, like, jump straight to the 15th number in the sequence because we don't care. So the sequence is all of numbers, and we can jump straight there to number 15 and so on. Okay. So I don't want to labor the point too much. I want to keep moving. Don't want this to get boring. So this is the kind of thing that we're doing with sequences. Okay. And as usual, they don't really tell you applications and stuff, right? but there are applications, of course. Okay, so now we have, yeah, so this second idea here is just a proof, but what we have here for this one here is a formula for Sn. So if we had a sequence, let's take like the previous one, right? So we had like A was equal to 4 and D was equal to 3. And then we had like, A15, which was equal to like, 4 plus 15 minus 1 times the 3, which ended up being 46. What if we want, so this was the 15th term in the sequence. What if we wanted to, calculate the sum of the first 15 terms? Well, how would we do that? Well, we have another formula to do this, okay? So what is it then? So it's n over 2. So it's 15 over 2, n over 2 times 2 times whatever a is, which was 4 plus, and then 15 minus 1 times 3. Okay. Now I can derive this formula for you. The first one is pretty straightforward, because you see what it's saying is it's saying here's your first number in the sequence, which is a, and then we add on d's to it to get the next terms, and this just tells you the number of d's that you have to add on. So it's the first term plus some number of d's, and it's always n minus 1, because the second term has got 1 d added on, the third term has got 2 d's added on, right? So it's like that. Now, this one here, this formula here is slightly different kind of derivation. Basically, what you do is if you wanted to add up all the numbers between 1 and 100, 1 plus 2 plus 3 plus all the way up to plus 99 plus 100, what you do is you take that line and you bend it around into a U shape. And what you have at the top is 1 and 100, and you have 2 and 99, and you have 3 and 98. And then you have, well, this is 101. This is 101. This is 101. They're all 101, and there's 50 of them. So it's 50. See, this counts up to 50, and this counts down to 51, and then we stop. So it's 50 times 101, and that's the sum. So it's 5,050. It's a little trick. It's like one of these maths tricks. Well, that's what that formula basically is. Okay, it's just another way of doing that. Okay, so now what we have sometimes is we have we might be given two terms in a sequence and their indexes, and then we might have to from that figure out what was the in order to be able to write down my arithmetic sequence, right? Now I might have to just given this piece of information to be able to recover. So what do I need from my arithmetic sequence? I need the A and I need the D. So that's what this question is really saying. So for example, when we start this question, we're just going to get together what we need. So we have AN is equal to A plus N minus 1 times D. Okay, so what they're saying with this first one is that N is equal to 5 and A5 is equal to 15. So let's do that. That's 15 is equal to A plus, sorry, I messed that up completely. Let me write that again. That's N is equal to 5 and A5 is equal to 17. Sorry. So over here, this would be A5, right? So A5 is equal to A plus 5 minus 1 times D. And then that's 17 is equal to A plus 4D. And we're going to stop there. Then we look at the second term. And for the second term, we have N is equal to 13. And we have that A13 is equal to 49. So this is going to be A13 is equal to A plus 13 minus 1 times D. And that's going to be, well, we know A13 is 49. So this is 49 is equal to A plus 12D. So this first thing that I have here, let me call it number 1 and call this number 2. And from working with this, I didn't get an answer for what A is and what D is. I need A and D to be able to write down this formula, right? Because Otherwise, I don't have a way. I don't know what the sequence is, right? So knowing what the sequence is being able to write down this formula. In other words, is finding those two for an arithmetic sequence. But what I have is I worked with this one, and this gave me this equation, and I worked with the second one, and that gave me this equation. So let me write the first equation: a plus 4d is equal to 17, and the second equation, a plus 12d is equal to 49. Okay. And what I have here is two equations and two unknowns. I have a simultaneous equation. Okay. So basically, if I only have one unknown in one equation, then I can solve it. But if I have two unknowns, then I need two equations to be able to solve it. If I have three unknowns, I need three equations to be able to solve it. If I have 10 unknowns, I need 10 equations to be able to solve it. Okay. So what do? We just say, let's make everything minus here, everything subtract everything here. So then this is a 0, and this is a minus 8d, and this is going to be, what's going to be minus 32, and then d is equal to minus 32 over like minus 8, which is equal to 4. Okay. And then if d is equal to 4, then we sub it back into one of them. So a plus 4 times 4 is equal to 17. A plus 16 is equal to 17. Bring the 16 across. A is equal to 17 minus 16. A is equal to 1. So I've solved it now because I have a is equal to 1, and I've got d is equal to 4. And now I can basically get anything here, and I can get anything here. Okay, so I've solved the sequence. Okay, so, and I think they will go on like this. Okay, so let's just, so they may give us it, like they can give us questions about, like, compound interest in the bank. It's another form of this and stuff like this. And what happens with those types of questions is they take us basically into the realm of like using like lots of words, right? So, okay, so they're saying 50 euro in the first month, so it's 50 euro in the first month, and then in the second month, we're going to increase this by 55, then it'll be like 60, and then it'll be like 65, and then 70. And we're going to do this for 12 months, right? So it's going to be, so we're going to say that, what do we want to say? So we want to say that figure out the total saved after 12 months. Okay, so let's just write out the numbers in the sequence. So 50, 55, 60, 65, 70, 75, 80, 85, 90, 95, and then 1, 2, 3, 4, 5, 1, 2, 4, 100, and then 105. Okay. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So these are just following that rule. So 50 saved in the first month, then 5 more each month from then on. And then it would just go on. Okay, on and on and on, apparently. And then what it's saying is find the total saved after 12 months. So this isn't 105. That's not our answer. Okay. This is 50 plus 55 plus 60 plus 65 all the way up to 105. So we have to add all of that's the series. So this is a sequence which is being generated by this rule, which is say 50 euro in the first month and then add 5 on each time. Then it's like add it all up. So it just gives you a little bit of an example of why we might want to do this. Okay, so we see that a is equal to 50, d is equal to 5, and we can just go ahead and apply these two formulas. So an is equal to a plus n minus 1 times d. So let's just try to get a12. That's equal to 50 plus 11 times 5. So that's 50 plus 55. So that gives us the 105. Okay, so that gives us that one. And then Sn is then going to be equal to n over 2, then 2a plus n minus 1 times d. If you ever wondering why I'm using square brackets now, all of a sudden, it's just basically when you have round brackets followed by round brackets and stuff, it can be hard to tell which bracket belongs to which. Okay, so this is n over 2, which is 12 over 2, and then 2 times 5, 50, sorry, 2 times 50 plus n minus 1, 12 minus 1 times 5. And you just work it out then. Okay. So let's move on because I want to get on to proof by induction. Now, the other way to generate a sequence is using geometric sequences. So this time we're going to start with a starting number and then multiply by OR, as I was saying. This formula here makes a lot of sense, right? So just have a look at what it is. So our first number would be A, and then we would multiply that by OR to get the next number. And then we would take the previous number, which is A OR, and then we'd multiply that by OR. But then the ORs would go together and it'd be like A OR squared. And then we'll take that last number, A OR squared, and then multiply it by OR. Okay, that would give me an A OR cubed, A OR to the power of 4, A OR to the power of 5, and so on. And what we notice about this, okay, this is the first term, A1 in the sequence, A2, A3, A4, or if you prefer, T1, T2, T3, T4. And look at the subscript in the power. See that this is, well, it's not there, is it? OR to the power of 0. This is OR to the power of 1. It's more obvious here. See, the subscript is 3 and the power is 2. The subscript is 4, power is 3, 5 and 4, 6 and 5. So you can see that it's always A times OR, and then we have a power that is just 1 less than whatever the subscript is. Great. So we can now use this. So if we start at this, A is equal to 160, and OR is equal to 0.5. And now we can work out A6 by using, that's going to be A, which is 160 times 0.5 to the power of 5, which is, we just put it into the calculator. Now, because the OR is less than 1, it's getting smaller each time. So A6 is going to be smaller than our starting number. Okay, so now how to do this now? Okay, so let's take the sum. So we have like A OR. Let's write the first n terms, okay? So we write down the first n terms of a sequence. A OR squared, A OR cubed, all the way up to A OR to the n minus 1. See that I'm not writing A OR to the n because then it would be 1, 2, 3, 4, 5, all of the n plus 1 terms, okay? So because this doesn't have any OR thing, it's like we have to have one less here. Okay, now the sum, Sn, would be A plus A OR plus A OR squared plus all the way up to A OR to the n minus 1. And just like really quickly, what I'm going to do is just take that sum, A plus A OR plus A OR squared plus all the way up to A OR to the n minus 1, and I'm going to multiply it by OR. I'm going to multiply OR by the whole sequence. So I get OR, so this is A OR. This is A OR squared. This is A OR cubed. Then it goes up, there's an A OR to the power of, there's an A OR to the power of n minus 1 and minus 1, and then an A OR to the power of n. And then what I do is I just simply shift it like so. And now I subtract. I'm going to subtract the first row from the second row. Everything becomes a minus. Everything becomes a minus. And everything cancels except for these two. So we end up having S minus OR Sn minus OR Sn is equal to A minus A OR to the power of n. And then I factorize out Sn into 1 minus OR is equal to A into 1 minus OR to the power of n. And then Sn is equal to A to the power of 1 minus OR to A times 1 minus OR to the power of n over 1 minus OR. Okay, so that's just the formula then, how you get it. Okay, so that's just the sum. I said I wouldn't derive it, but it's just quick to do it. The reason why OR is not equal to 0 is because then we would be dividing by 0. Okay. And the last thing that we'll say is about S infinity. S infinity. Let me give you an example. So there is, let's say, here's a table. Let me draw it properly. This is just a riddle or whatever. So we have a table, and in the middle of the table, we have a frog. Okay, so the frog is told to jump off the table. Let's say this is 1 meter or something like that. And the first jump takes the frog half the way. And then the rule is every jump is half the previous one. So this is a quarter of the way, then an eighth of the way, then a 16th of the way. And the question is how many jumps to get off the table. And basically what happens is that the frog never gets off the table, right? Another example is the following. Another way to talk about the same thing is to say, like, imagine if you have a square like this. Yeah, okay, I'll do it that way. So, okay, so let's take half the square. Okay, now take half of that half. Okay, now take half of this half. Now take half of that half. And now take half of that half. And now take half of, I didn't do that right today. Now take half of this half. And so what you can see is that there's always like a little bit left over, right? So you see there's always a tile in the middle that we don't fill. And as we go on, like what'll happen is that we'll keep sort of going in like this, you see, but we'll always have one little tile that gets smaller and smaller and smaller. So this is an example of a half plus a quarter plus an eighth plus a 16th plus 1/32. And they keep getting smaller and smaller. And this thing actually, when you add up the sum, and this would be the infinite sum, like if you could imagine adding up every single number in the list, you get that equal to 1. Okay, now how do we get that? Well, we have a sum to n, which is a times 1 minus or to the power of n all over 1 minus or, okay? And what we're going to do is we're just going to realize that basically as n goes to infinity, or to the power of n goes to 0. This is kind of easy to see, right? When this only happens when the absolute value of or is less than 1. Like, for example, think of a half, okay? That's, okay. Now a half squared, like a half squared, that's going to be a quarter. Then a half to the power of 3 will be an 8, then a 16, then 1/32, then 1/64, then 1/128. So that bottom number, the denominator in the fraction keeps getting smaller and smaller and smaller, okay? And that's why it's getting, so basically if that n goes to infinity, that means that the denominator in the fraction here gets infinitely large. So you got 1 over like a huge number, right? That keeps getting bigger and bigger and bigger. So that's why it goes to 0. And so basically here we can say that as n tends to infinity, basically Sn tends to a plus 1 minus 0 over 1 minus or, because this thing here goes to 0, and that's just the same as a over 1 minus or, okay? So if we ever want to work out the infinite sum, so we can take an infinite sum, like, so we can add up an infinite list of numbers, but we can only do that when that or for a geometric series is less than 1, okay? So, and I think that's basically, so let's say, for example, we have an example like, let's take this one. So we've got a is equal to 2, and then or is equal to 3/2. So in order to, and then, yeah, so then because if we want to go from here to here, we have to multiply by 3/2. If we want to go from here to here, we multiply by 3/2. And this 3/2 is greater than 1. So that means that this series, this sequence or the series, which is the sum of the sequence, I mean, diverges, right? So the numbers keep on getting larger and larger and larger. So if we try to add them up, it wouldn't give us a finite number. It would go to infinity. But this one here, a is equal to 1, and then or is equal to a half, because this is that's 1 by a half is a half. Okay, so this here is the series. The actual sequence is this, right? 1/8, 1/16. So this, and then adding them up is the series, and we can see the or is less than 1, so we can say the infinite sum is equal to a, which is 1 over 1. Sorry, a over 1 minus or, so a over 1 minus a half. This is 1 over a half, and then 1 over a half is equal to 2. So the infinite sum of a number starting at 1 and then multiplying by half each time, when you add up all those numbers, it ends up getting 2. Okay, so you have some more to do in sequence and series. That's not the full summary, but it just gives you a refresher on the two main there isn't another, like what can happen on the leave insert is that you may be given a sequence and you may have to just work out, they won't have a name. It'll just be like work out. So you might have to say um, like come up with an expression, like come up with something like a formula for a given sequence, right? So that's the other type of question that you get. But I'll be doing all of the exam questions starting from September, so I'll come across them in time. Okay, so the next thing that we're going to talk about in the time remaining is to talk about proof by induction. Okay, and okay, so let's just talk about two different forms of let's say extrapolating some fact or like proving something. So the first way is the sort of Sherlock Holmes thing. Here's my magnifying glass. Deduction. Okay. So for deduction, you have to basically collect lots and lots of different pieces of information that when you get enough of them, they all basically point to the same thing. And that's the way to prove the fact, because you've deduced it. You've sort of you're kind of going down. But induction is actually the opposite effect. You're going to start with like just a couple of things, and then that's going to make the next thing happen. That's going to make the next thing happen. That's going to make the next thing happen, and then it's just going to keep on going. So induction is only really possible in mathematics, right? So if you're inducing something in real life, you're probably jumping to conclusions, right? You probably haven't gathered enough evidence. You're probably like it's like a childish kind of thing. Like, I don't know, if you imagine a baby, I don't know, sees the postman coming and it rains, and you say, oh, every time the postman comes, it rains, right? That would be a way to induce something about the world from just one sample or something. So induction only really works in mathematics. And the way to think about it is to think about, I think I've got some pictures here before, is just to think about dominoes. That's the way I think about it, right? So you're basically everything has to be sort of set up basically in a kind of a line. And then you have to go about proving two things. Okay. What you need is two things. You need to kind of show the first thing. And that for us, that would be like the equivalent of knocking that first domino. Okay. And then what happens is that first domino, after being knocked, has to knock the second domino. And that has to be true for all the way along the list. Okay. So we'll see this in practice now in a second. Okay, so that's the idea. Okay, so let's have a look at how we're going to go about doing this. So okay, so there's basically three steps to this. Okay, so let me just write this. So the first thing that we want to do is we want to prove this for a base case. Right, so we want to say basically we're going to set n to be equal to some number in our proof. It could be one, usually it's one, it could be two, it could be three. It doesn't matter. We just have to prove that it works for a base case. So that would be like the first domino. So all my dominoes are set up here. And what we want to say is we want to say something is true for an. This is what we want to prove. Okay, like we'll see in a moment what it is. And this will be A1, A2, A3, A4, A5, and so on. Okay, so we want to basically prove that the thing works for like a base case, like prove that it works for a base case for n is equal to 1. And then we have what's called it's the induction hypothesis. We want to, we basically assume that it's going to work for some random number along the list that we're going to call k. So in a sense, n here is distinct from k. This always sort of like kind of muddled me up when I was younger, like kind of doing this stuff. Like, why are we introducing a k here? Well, we saying this n is equal to k. And the reason is that the n basically relates to all of these. It just relates to the full list, if that makes sense. And then what we want to think about with this k is that this k is just somewhere in the list. Okay, so that we call that one k. It's just somewhere in the list. It doesn't matter. Wouldn't matter where it is. Could be the first one, could be the second one. And then what the proof is we show that if it's true for k, then it's also true for k plus 1. This means that if this one is true, then the next one is true. So we show it's true for the first one, but because of this thing that we just proved, that would mean that it's true for the second one. Because it's true for the second one, it's true for the third one. And then it just goes down the list like dominoes. And then you can say that it holds for all n, and then we've proved it, okay? So let's take an example here. So I want to just take this one here. Okay, so this is what we want to prove, that the sum of, yeah, it's a bit awkward. Like, what I think is awkward about this is the fact that we've got n's, we have n's and k's, and like j's are here and stuff like this. So it just, but if we just sort of follow it, see what it works like. So what we want to say is that the sum of this thing, that the sum of k, for k is equal to 1 to n, is equal to n times n plus 1 over 2. Okay, what is this? So the sum of k from k is equal to 1. Okay, let's write this out. The sum of k from k equals 1 to n. Well, let's say k was equal to 1. That would be 1 plus, and then now k is equal to 2, plus, now k is equal to 3, plus, all the way up to n. See, we're taking the sum, which is all of these plus signs, of all the k's, and the k's are going from 1 to n. So it's just 1 plus 2 plus 3 plus 4 all the way up. Now this is like we can see immediately that this is a sequence, right? 1, 2, 3, 4, 5, 6. So it's based on the sequence all the way up to n, so on. And we're taking the sum of that sequence. Okay. Now what we want to show, right? What we want to show is that the sum of that is equal to n times n plus 1 divided by 2. Now we could show that if a was equal to 1, see d is equal to 1. That's our first number is 1. All of the gap between every number is also 1. Okay. So we could go ahead and use the formula that we had like here in order to do that. But we're going to do it by induction. Okay. So here's the 3 things that we need to do. 1, 2, and 3. And for every example of proof by induction that you do, this is going to change. Like what you're trying to prove is going to change, right? You're going to use it to prove like lots of different things. But these 3 steps will never change. So we want to show a base case. Usually that's n is equal to 1. We want to assume for some random number in the list that we just call k. And we may get muddled with the fact that we're already using this k here, but let's just proceed anyway. And then we want to show that if it's true for whatever n is equal to k, then that implies that it's true for n is equal to k plus 1. Okay, so let's have a look at this here. And let's go through the cases. So let's take n is equal to, let's take n is equal to, well, we take n is equal to 1 and try to apply this formula. So the sum of from k is equal to 1 to 1 of k is equal to 1 times 1 plus 1 over 2. It's 1 times 2 over 2. It's just 1. So if we go along this list here, the sum of the list, just when we only go up to n is equal to 1, so only the first number on the list is equal to 1. That's enough. We've shown the base case. Maybe it doesn't feel like enough, so let's do n is equal to 2. The sum from k is equal to 1 up to n, but n is now 2 of k is equal to, let's look at the formula, n times n plus 1 over 2. So that's 2 times 2 plus 1 over 2. The 2's cancel. This is 3. That's the same as 1 plus 2. Yes. So that's the sum. This is like S2. This is like S1. Okay. I hope that's clear that we've now shown, doesn't matter which base case, but we've shown for a base case. So we've done this step here. Now, this is the part where maybe the way this is, Written is a little bit awkward. We can find another. So let's have a look anyway. So now we're doing step 2, and we want to assume for n is equal to k, some number in the list. Could we change our thing to be like? So I don't want to confuse you, which this is why I'm pausing. It's just a little bit. So this is what I have to say here. See that we're introducing the j now? We're only doing this because j is equal to 1 to n of k. Is it? No, sorry. What is it? J is equal to 1 to n of j. And what we're going to say is, so n is equal to k, so then we say, so what this is now is basically saying, the problem is that we're kind of using this k twice in two different, here it was inside and now it's up here and it's with j now, and you might be thinking like what's going on here or whatever, which is totally understandable. So all we're saying now is that we're going to take the sum, we're going to go up this list. See, we went, the sum up to 2 was here, so that took us up to there. And then we're going to take the sum up to somewhere, let's say that's k. So that would be 1 plus 2 plus 3 plus all the way up to k. And this is how we're writing it. And then basically the answer then is k times k plus 1 over 2. And we're going to assume that that's true. So this is not, we're just assuming that it's true. We don't know that it's true. Okay, so now we come to step 3. And this piece here, this is called the induction hypothesis. Basically, your assumption from part 2 is going to go into part 3. That's how this thing works. Okay. And then for step 3, so now we're going to show for k plus 1. So for k plus 1, j is equal to 1 of j up to k plus 1. This is then going to be, well, it's going to be this formula again. So you see the way that n is there, and then there's an n here, and there's an n plus 1 here, and then there was a k here, and then there was a k here and a k plus 1. So what we need to do is put whatever that number is here first, k plus 1 over 2. See, it was k plus 1 times the n plus 1. So k plus 1 will be k plus 2. And then this is all over 2. And this would be k times, so this is here on the top line, k times k plus 2 plus k plus 1 times k plus 2 all over 2, which is the same as k times k plus 2 over 2 plus k plus 2 over 2. Okay, now this one here, using step 2, this is when what we have from step 2, the induction hypothesis comes down. This is the sum up to k, right? So this is the sum of j is equal to 1 to k of j plus k plus 2 over 2. Did I do that right? Sorry, I multiplied this out wrong, didn't I? Oh, yeah. Sorry. I did that. Let me just go back. 1 second. Sorry about this. I think I got caught out because I used this J here. The example, I'll get an example from the exams now, just to. Okay, sorry. So what I'm going to do now is I'm going to multiply out this k plus 2 is going to multiply out this thing. So I have a k times k plus 1 plus a 2 times k plus 1. Okay, so just multiplied that by this set of brackets, and then that by this set of brackets all over 2. Now this is k times k plus 1 over 2 plus 2 times k plus 1 over 2. And by the induction hypothesis, this thing is just a sum up to j. J is equal to 1 to k. And then this one here plus the second one, which is just k plus 1. Okay, so we've actually proved it. Why have we proved it? Right? The reason why we've proved it is because let's say that the sum up to k is equal to this thing. Well, the sum up to k plus 1 would just be that same thing plus k plus 1, plus the next thing. See, we're summing all the way up until we hit k, and then we would get whatever that answer is. And then when we add on the next term, then it's just going to be whatever the previous answer was plus the k plus 1, which is what we found. Okay, that might not seem obvious. So let's try to find. We have enough. We've got 5 minutes, so I can do a quick exam question. So let's see if I can find one. So we see if we can find a nice example. That was the same one. Okay, so let's take this one here. This is probably a nicer one. See, they're always different, these ones. And we'll also just quickly take over the solution. I don't want you to go away thinking that induction is harder. That wasn't my purpose. So I want to try and let's take this second example. And then we'll. Now, when you see one of these examples, you're never going to like know exactly how to do the question, right? So you're always going to be a little bit unsure of what to do when it comes to proof by induction. However, what we're going to do is we have the claim, right? So this is the claim. Prove that 13 to the power of n minus 1 is always divisible by 3. This is what we want to show, okay? So how are we going to do this? Well, step 1, that's what we wrote up here, base case. Number 2, assume for k. Number 3, show 4 k plus 1. Okay, base case. Let's take n is equal to 1 and ask ourselves, is 13 to the power 1 minus 1, is this divisible by 12? That line there, incidentally, means divisible. I don't know if you use it, but it's a big straight line like that. 13 minus 13 power n minus 1 is divisible by 12. Is that true? Well, this here is equal to, that's equal to 12, and 12 is obviously divided by 12, so it's true for the base case. So we've done the base case. Now we come to step 2. Step 2, assume for k. That means 13 to the power k minus 1. This is divisible, I'll put it in brackets, by 12. Okay, so we don't know that this is true, but we're going to assume that it's true. This is called the induction hypothesis. So remember, like a hypothesis is like, like it's like, let's go with this. This is my idea. It's like an idea. We're going to go with this, and we're going to see where it takes us. And if we end up, our next step can show that the previous assumption was correct or not correct. Okay, so now we're going to show for k plus 1. Okay, so what's this for 13 to the power k? Well, let's start working on the left-hand side. So 13 to the power k plus 1 minus 1 is equal to, well, just knowing our laws for indices is 13 to the power of k times 13 minus 1, which is the same as 13 to the power of k times 12 minus 1 minus 1, which is 13 to the power of k, well, 12 times that, okay, 12 times that, minus 13 to the power of k, and then which is, sorry, This is not 12 minus 1. This is 12 plus 1. Sorry, 12 plus 1 plus 13. Sorry about that. This 13 here, I broke it into 12 plus 1. Then minus the 1. Okay. Okay. And now we're finished. This is divisible by 12. Why is this divisible by 12? The reason is that this piece of it is divisible by 12 by the induction hypothesis. Right? We didn't show it at the previous part, but we're kind of like, we're just going with this now. We're going to say that like from step 2, this is the induction hypothesis. So we're just assuming that this is true. So this is true by assumption. And then look at this piece here. This piece is definitely divisible by 12 because it's multiplied by 12. So this piece is divisible by 12. This piece is divisible by 12. And we have two things that are added together that are both divisible by 12. So the whole thing is divisible by 12. Okay. So like we can say like 4 is divisible by 2 and 6 is divisible by 2. So this will be divisible by 2. Okay. So, okay. I'm going to finish there. I'm going to finish there. I've got another class coming up. I hope that was helpful. The examples, let's just have a quick look. Like the examples that you get, you can kind of see that they're always different, but proved by induction. But they may always be different, but I always have these 3 steps. And then step 1 is just to show for base case. Step 2, assume for k. And then step 3, this is where the real work happens. And you just have to sub in k plus 1 in place of the n usually, okay? Okay, so we'll leave it there. Yeah, thanks for joining me. And then we'll continue on then tomorrow at the same time. I'll send you some notes. I'll send you the video to this, a recording of this afterwards. And then, then I'll send you a reminder for the lesson tomorrow. So have a nice evening and I'll see you tomorrow.